All right. My name is Woody Claremont. I'm presenting my data analytics graduate capstone for the C772 class. My topic for this capstone will be increasing life expectancy. So, life expectancy, simply put, is an estimate of how many years on average we might expect the average person to live to. And so, as a result, more people want to extend their longevity as long as possible because obviously we don't know what comes next. Um, but nonetheless, we'd like to make the most of our time on Earth as it is. And so it would be beneficial from a standpoint of a government like the state of Florida, which is I am a resident of, a proud resident of, to look into ways into which they can benefit their citizens or residents by promoting programs and initiatives that would go towards extending life expectancy. There are 67 counties total in the state of Florida, and the state government itself has oversight as a whole of these 67 counties. So therefore, the type of remedial change that we're looking for would occur both at the state level as well as the level of the local counties. So, what is my research question? My research question would be, quite simply put, what factors are more strongly correlated with a change in life expectancies? In other words, if we treat each county as a cohort and we examine the data from each county with regards to life expectancy and with regards to factors that we can look at and study, what factors are going to be more strongly correlated with change? So therefore, our null hypothesis is going to be that all study factors do not affect life expectancies and that we will see no significant differences in these life expectancies. But the alternative hypothesis, should we find evidence to reject the null hypothesis, would be that some study factors, not necessarily all, but the ones that we are able to determine do have an effect, can affect life expectancies either positively or negatively, and that there will be statistically significant differences in those life expectancies if we encounter changes in these particular factors of question. So, what was the process that I underwent in order to conduct this data analysis? Well, there are, quite simply put, 5 things to go through. The first being that we define our question, we develop the hypothesis. We've already done that. So now we have the other 4 items that are before us, which is that we decide what to measure and how to measure it, that we collect data, extract and clean the data, that we analyze the data, that we interpret the results and apply them to our ultimate goal, our research question, hypothesis. And so as far as step 2 goes, deciding what to measure and how to measure it, you're going to see in the slides that follow that I tended to go with factors that could be expressed either in percentages, that could be expressed as an index, or that could be expressed as a rate. And so, therefore, it was easy for me to measure these items because they all followed different scales, which were easy to work with. As far as collecting the data, extracting it, and cleaning the data, what I in fact did was I used a website, which is at the University of Wisconsin Population Health Institute, which is primarily funded by the Robert Wood Foundation. And I looked at data which was provided, which has been aggregated from multiple sources. Some of it may come from the Census Bureau, some of it may come from the CDC, some of it may come from a variety of other places. So this would be considered to be secondary data, but it would be third party because of the aggregation from different sources. And pretty much all of the data was quantitative. Then I analyzed the data, and I'll show you in the upcoming slides how exactly I did analyzed the data, and then I interpreted the results. So moving along, let's go into the measurement and the data collection. As I told you before, State of Florida has 67 counties in total. And for purposes of my study, I had to use those observations which had a life expectancy value associated with them. Unfortunately, with the data at the University of Wisconsin Population Health Institute, only 2019 and 2020 were available. So therefore, I had to work with the data which they had gained in the preceding years, which were 2018 and 2019, in order to produce the data set that I could use to import into what would ultimately be SAS, which is a professional service that is well known. It is extremely beneficial. It's well tested. It's commercial software to analyze the data in terms of the independent variables and the dependent variables. Just by way of examples of what constituted the dependent variable, obviously that's going to be life expectancy. In terms of independent variables, I looked at factors like percentage of frequency of emotional distress, percentage of frequency of mental distress, percentage of adults with diabetes, number of HIV cases, percentage that the food would be insecure, percentage of those with limited access to exercise opportunities. Even demographics like percentage that were Black or African American, percentage that were Asian, percentage that were Native Hawaiian or other type of Pacific Islander, percentage that were Hispanic, percentage that were specifically Hispanic and white. Additionally, percentage of children in poverty, percentage of unemployed, in the income inequality rate, the income ratio, the degree of social association, percentage that were obese, presence of water violation in a particular county, percentage that were housed in locations that encountered severe housing problems. Also, I collected the data primarily through Excel because that's how it was available on the website. And I made sure that all of the data conformed with SAS's rules before importing the data to SAS. When I did import the data to SAS, then I had to engage in some cleaning by remedying the problem that there were some missing values, that some counties hadn't fully reported their statistics. In particular, there was a drug overdose mortality rate, which some counties did not report. There was a homicide rate that some counties did not report, and there was a firearm fatalities rate that some counties also did not report. So I ran an SAS procedure called PROC-ME, which allowed me to impute those missing values. Standard text might recommend a mean or median imputation, but I actually ran an imputation which was based on regression itself, which took the values and was able to estimate what the predicted values would be for the missing values for the counties. And so as a result, that was able to take care of those problems. The only other transformation I had to do was that one particular variable, which was the presence of water violation, was usually answered as yes or no. And so that being a qualitative variable had to be converted to a quantitative variable. So therefore, I converted all of the no's to zeros and all of the yeses to ones. So now I went to the process of actually beginning the data analysis. And with that, I started analyzing the individual predictors. I ran a univariate analysis on each independent variable, and I obtained basic statistics. Statistics like the mean, the median, standard deviation, the variance, the quantile determinations, the ranges, notes of the 5 extreme variables on the upper end and on the lower end, and histograms to determine the spread of the values to determine whether or not I would have any significant problems working with these particular variables. I also did a study of outliers and influential observations, because obviously this can also have a significant impact on our data analysis. So I used the influence diagnostics to look particularly at DF fits and DF betas, to see whether or not, as each individual variable impacted life expectancy, which outliers were beyond a certain range, usually particularly an interquartile range. And so as a result, after studying all of the results, I was able to determine there was nothing alarming or concerning about the variables, that I could proceed with the analysis as intended. And in terms of what type of analysis I chose to do, I chose to go with linear regression. Linear regression has the advantages of being very simplistic and straightforward to use. A lot of it relies on linear algebra and on matrices in terms of basically determining relationships between the data points and the means and the dependent variable itself. And therefore, I would be able to determine the relationships between the different predictors and the target variable. And then I would also use model selection to kind of whittle down, because initially I had roughly around 48 different variables to work with, but obviously this would be cumbersome. We don't want our models to be bloated and to have unnecessary variables that are included. We want to try to have a regression equation that's accurate and that's very parsimonious, so that we don't have irrelevant predictors contributing to our equation. So I had to also make sure I verify the assumptions of linear regression, which are linearity, homoscedasticity, independence, and normality. Obviously, linearity refers to the fact that the independent variables actually have a linear relationship with the dependent variable. Homoscedasticity refers to whether or not there is constant variance in the residuals. Independence is that the observations themselves do not overlap with one another, that they're in fact statistically different and independent from one another. And normality would reflect that, in fact, the residuals were normally distributed, that they didn't follow any particular patterns that would cause a problem. And so for the model selection in SAS, I use the ProcGLM select procedure with the stepwise selection method and the Sawa-Bayesian criterion, SBC, and the validate option, which basically chooses the model based on the lowest average squared errors, ASC. And obviously you can see there are some small graphs here which kind of show highlights of what I encountered. We also have the SBC formula there itself, which shows you how they determine the SBC score. And usually part of that determination involves a natural log of a particular number. In this case, it is the sum of square errors divided by the number of observations, but also with penalties based on whether or not you might have, say, too many predictors. So when it's comparing different models in terms of choosing which model will be the best, it's going to penalize necessarily models that are variable heavy, that have too many variables that are unnecessary, and it's going to reward those models which are more parsimonious and which are highly accurate. So here are our results. And on the left here, as we can see, we have an adjusted R-square value, which also is good for making sure that we don't have more variables in our model than we should. And based on that number 0.7859, we know that 78.59% of the variation in the dependent variable, which is life expectancy, is explained by movement in the independent variables. And we know that in terms of the F-test for significance of the regression itself, that our value of 123.04 shows that this is extremely significant, that we're able to reject the null hypothesis that we would be better off using a regression with a bunch of zeros in the coefficients, and that in fact these particular parameters that we've estimated in fact do better. They do so much better that our p-value is less than 0.0001, which expresses high extreme statistical significance for this regression. Likewise, the t-values for each portion of the regression equation also are all statistically significant, including the intercept. Right? For the intercept, we have a t-value of 118.88. For the first interaction, we have 10.02. The second interaction, negative 12.97. Third interaction, negative 5.76. The fourth interaction, negative 3.78. And all those have extremely low p-values. The intercept in the first three lower than 0.0001, and the last being equal to 0.0002. And we also have our standardized estimates as well. And we also went ahead and examined the variance inflation factors to just verify that we don't have any issues with correlation amongst the variables itself. The numbers are all extremely low. They're lower than 10, so we're not going to have a major problem there. On the right, I have the fit diagnostics. The first being the residual against the predicted values, and that tends to show us that, in fact, we don't have any issue with homoscedasticity. Then we also have our QQ plot and our histogram, which tends to verify that, in fact, the data is normally distributed. The residuals are normally distributed. We have our middle plot, which shows that the values are highly clustered around the diagonal line. That satisfies our assumption regarding linearity, so we're good there as well. So overall, and based on the fact that when we designed the study, we made sure that all of the observations were independent from one another. We do not have a problem with meeting all four assumptions for linear regression. So going to the next slide, outline of the findings pretty much confirm a lot of what I've discussed. In this particular illustration here, what I've actually done is I have treated each variable as a singular variable in the regression equation to go ahead and just make sure that every variable was itself statistically significant that was involved in the four interactions that we saw on the previous slide. And as we can see from the t-values and the p-values, they all are. They all are at least meeting the alpha equals 0.01 or alpha equals 0.001 level in this case. So therefore, every term is extremely statistically significant, although the PROC GLM Select actually recommended the model with the interactions because the interactions were even more so statistically significant than the variables by themselves. So moving along, what are our findings? The findings are that uninsured adults, right? We had a percentage of uninsured adults that has a positive relationship with life expectancy. That teen birth rate, percentage of those with insufficient sleep, injury death rate, and a percentage of those who are smokers have a negative relationship with life expectancy. That all these predictors are statistically significant even when alpha equals 0.001. And we're able to reject the null hypothesis from our original research question, and we can accept the alternative hypothesis that some of the study factors which were outlined do correlate with changes in life expectancy, which answers our research question. So what are some of the limitations of the techniques and tools that I used? Well, obviously, first off, to start with, it would have been nicer if I had more data to work with. I explained how we only had 2 years available, 2019 and 2020, which were all drawing data from the previous year, 2018 and 2019. And so it would have been nice if we could have had more years going further back. But as time progresses, the University of Wisconsin Population Health Institute is going to be able to create additional data sets for 2021, 2022, going forward, that eventually we may have up to a decade of data by 2029. Also, it would have been beneficial if we could maybe have used other states rather than just Florida for purposes of our study. Maybe other states that had similar patterns to Florida that would have made them relevant to our analysis. Linear regression can also be problematic when overfitting occurs. In other words, sometimes there may be additional interactions that are going on that we may not see. And so if we're fitting the data too closely to our particular terms in our equation, there may be more of the picture that we're missing. Confounding variables also could be an issue. They may not have been fully identified, and when the predictors here are based on incomplete information like that, then we would say that's a spurious association that might be going on. Because if we had those additional variables, we might find that our analysis would change dramatically. Not all variables may be linearly separable in the real world. That goes back to our assumption of independence. We indicated that by the design of our study that we believe that none of the observations overlap with each other. But that may not always be the case in the real world, and so we need to watch out for that. Also, linear regression may inaccurately reflect the relationship if the actual association is nonlinear. For the most part, based on the way our results turned out, it looked like it was a very nice relationship that we could express in terms of linear regression. But maybe further studies we could find that there is some sort of a nonlinear association hiding in there, and maybe that would better fit the data and the results. Also, lastly, that correlation is not causation, and that if we are making these assumptions about the relationship between the variables, the independent variables and the dependent variable, that we have to be careful that all we've seen is a relationship, a correlation. We've not actually seen evidence of actual causation. We would actually need to run different tests in order to determine that. So what actions should we take in response to these results? Well, first off, to remedy the problem of uninsured adults, the state of Florida could go beyond Medicaid expansion and see about legislating and enacting single-payer health care to provide more of this benefit to Florida citizens, because obviously with being more proactive about health care, we might find our citizens living longer. To remedy the problem of smoking, the state could also fund more tobacco control programs to focus on finding more ways to eradicate tobacco use in Florida. To remedy the problem of teen births, we have more multi-component and community-wide initiatives that could be developed to reduce the rate of teen pregnancy. To help with lack of sleep, we could have the state fund more programs at academic health centers and make more medications and therapies available to Florida residents. And lastly, to remedy the problem of accident injuries and deaths, Florida can study how to eliminate more crash risks on the roads and highways, and to find better ways to regulate the workplace so as to reduce the hazards and decrease the prevalence of workplace accidents. So from a quantitative standpoint, let's look at how our regression worked. The percentage of insufficient sleep multiplied by the percentage of uninsured adults impacted life expectancy in a positive way. For every 1 unit change in this interaction, that we would find a 0.010796 increase in life expectancy. Our interaction of percentage of insufficient sleep times percentage of smokers had a negative relationship. So for every 1 unit change in that, we would find life expectancy would decrease by 0.013386. We have percentage of uninsured adults times the teen birth rate. And so for every 1 unit change in this interaction, we would see a decrease in life expectancy by 0.003634. And our percentage of insufficient sleep times our injury death rate. For every 1 unit change in this interaction, we would find an decrease in our life expectancy by 0.000607. We also have our standardized estimates as well for you to look at. And so these would be the expected benefits in the long term, that if we want to increase life expectancy, we should decrease those things which have a negative impact and increase those things which have a positive impact. Lastly, I have my references of the different sources that were used: Saltz and Stanton, the SAS Institute, SAWA, particularly regarding the SBC that was used earlier, Teferi in terms of Understanding the Data Mining and Analysis Process, and the University of Wisconsin Population Health Institute, from which I drew my data. That's all for my presentation. I hope you've enjoyed, and I hope this has been very informative for you. Thank you, and goodbye.